Alright, let's tackle this cubic equation problem together. We're presented with this equation, t3 plus 4t2 plus 4t plus a equals sign 0. The problem tells us that it has 3 real roots, and these roots are ordered. That means one is less than the next, which is less than the third. Let's call them x, y, and z, where x, y, z. What does this equation represent? Well, it's a cubic polynomial, and when a cubic polynomial equals 0, that signifies the values of t that make the equation true. Those are the roots. Now, we are asked to find the range of values for an expression a, which is a equals sign x3, 4y2, 4z2, 4y, 4z plus 32. Sounds complicated, right? Don't worry, we're going to break it down systematically. The key here is to connect these roots, x, y, z, with the coefficients of the cubic polynomial. And that's where something called Vieta's formulas come in. Vieta's formulas give us relationships between the coefficients of a polynomial and its roots. Let's review them for a general cubic equation of the form at3 plus bt2 plus ct plus d equals sign 0. The sum of the roots is ba. The sum of the products of the roots taken 2 at a time is cea, and the product of the roots is dA. In our specific equation, t3 plus 4t2 plus 4t plus a equals sign 0, notice that a equals sign 1, b equals sign 4, c equals sign 4, and d equals sign a. So, applying Vieta's formulas, x plus y plus z equals sign 4 over 1 equals sign minus 4. Also, xy plus xz plus y's equals sign 4 divided 1 equals 4. And finally, xyz equals sign a1 equals sign a. These 3 relationships are absolutely crucial. They're our bridge to connect the roots and the expression a. Okay, let's look at the expression for a again. A equals sign x3, 4y2, 4z2, 4y, 4z plus 32. The problem mentions something about using the polynomial equation itself. What does that mean? It means we can substitute x into the original equation. Since x is a root, when we plug x into the equation, we get 0. So x3 plus 4.2 plus 4x plus a equals sign 0. Therefore, x3 equals sign 4.2, 4x, a. That's a really useful piece of information. Now let's substitute that into our expression for a. We replace x3 with 4.2, 4x, a. So a becomes a equals sign 4x2, 4x, a, 4y2, 4z2, 4y, 4z plus 32. Let's rearrange this a bit. A equals sign 482, 4y2, 4z2, 4x, 4y, 4z, a plus 32. Notice anything interesting here? We have 4x2, 4y2, 4z2, 4x, 4y, and 4z. We'll need to use the Vieta's formulas to simplify this further. Let's think about what we can do with y2 plus z2. We know that x plus y plus z2 equals sign x2 plus y2 plus z2 plus 2, xy plus xz plus yz. We already know that x plus y plus z equals sign minus 4, and xy plus xz plus yz equals sign 4. So, minus 4, 2 equals sign x2 plus y2 plus z2 plus 2, 4. This simplifies to 16 equals sign x2 plus y2 plus z2 plus 8. Therefore, x2 plus y2 plus z2 equals sign 8. This means y2 plus z2 equals sign 8, x2. Now we can substitute that back into our expression for a. A equals sign 4.2, 4.8x2, 4x, 4y, 4z, a plus 32. Let's simplify this. A equals sign 4x2, 32 plus 4x2, 4x, 4y, 4z, a plus 32. This simplifies to a equals sign 4x, 4y, 4z, a. Factor out the minus 4, a equals sign minus 4, x plus y plus z, a. And we know x plus y plus z equals sign minus 4. Substituting that in, we get a equals sign minus 4, a. Therefore, a equals sign 16, a. So the expression a is simply 16 minus a. That seems almost too simple. But this means the range of a depends entirely on the range of a. To find that range, we need to think about what makes it possible for the cubic equation to have *3* real roots. Think back to calculus. When does a cubic equation have three real roots? It has to do with the local maximum and local minimum values of the function. We need to think about how to express it in terms of t. From our original equation, t3 plus 4t2 plus 4t plus a equals sign 0, we can write a equal sign t3, 4t2, 4t. Let's call this function ft equals sign tt3, 4t2, 4t. To find the local maximum and minimum, we need to take the derivative of ft and set it equal to 0. ft equals sign 3t2, 8t, 4. We need to solve 3t2, 8t, 4 equals sign 0. This is a quadratic equation. Let's solve it using the quadratic formula. T equals sign b plus b2, 4ac, 2a. Here, a equals sign minus 3, b equals sign minus 8, and c equals sign minus 4. T equals sign 8 plus minus 8, 2, 4 minus 3 minus 4. 2 minus 3 equals sign 8 plus 64, 48, minus 6 equals sign 8 plus 16, minus 6 equals sign 8 and 4 minus 6. So our two critical points are t equals sign 8 plus 4, minus 6 equals sign 12, minus 6 equals sign minus 2, and t equals sign 8, 4, minus 6 equals sign 4, minus 6 equals sign 2/3. Now we need to find the values of a at these critical points. When t equals sign minus 2, a equals sign minus 2, 3, 4 minus 2, 2, 4 minus 2 equals sign minus 8, 4, 4, plus 8 equals sign 8 to 16 plus 8 equals 0. So for the cubic equation to have three real roots, a must be between 0 and 32/27. This means 0, a, 32/27. Therefore, since a equals sign 16, we can find the range of a. When a equals sign 0, a equals 16 minus 0 equals sign 16. When a equals 32 divided 27, a equals 16 to 32 divided 27 equals sign 432, 32, 27 equals 400 divided 27. Therefore, the range for a is 427, 16. This problem highlights the importance of understanding the relationship between the coefficients of a polynomial and its roots, and how calculus can be used to determine the number of real roots. The critical points represent local maxima and minima, and the constraints on a ensure that the function crosses the x-axis 3 times, leading to 3 real roots. Ultimately, this exercise demonstrates how abstract mathematical concepts can be applied to solve practical problems and gain insights into the behavior of complex systems. This connection is critical to truly grasping the usefulness of these techniques. The problem uses Vieta's formulas, which relate the coefficients of a polynomial to sums and products of its roots. While they aren't directly used to find the value of a, they demonstrate the intricate relationships between a polynomial's coefficients and its solution set. Furthermore, we leverage calculus by taking the derivative of the function, finding critical points, and evaluating the function at those points. This allowed us to determine the constraints on a that would guarantee the existence of 3 real roots. It is important to remember that the number of real roots of a polynomial equation is intimately tied to the shape of its graph. The constraints on a ensure that the graph crosses the x-axis 3 times, signifying the existence of 3 real roots.